Hi, I'm Jonathan Aldrich. Let's talk about polymorphism and type inference. Polymorphism, also called generic types, allows one function to work with multiple types of data. Let's look at an example of polymorphism in Java. Here we have the isMember routine that checks whether some value is a member of some array. But what type is the value and what type is the array? They ought to match, but it really could be any type. So we'll call that type t. T is a type parameter, and in this case, it's the type parameter of the isMember method. In Java, we write the t in little brackets before the return type of the method. Now, I've grayed out the code. You can see what it does, but it's pretty ordinary Java code. We're just iterating through the array and checking equals on every object in the array. But the important thing is that we can type check this, and we can make sure that the value we're checking for inclusion in the array is of the same type as the array is. Let's look at how this code is used. Imagine we have an array of integers, 1, 2, 3, and an array of strings, hello and world. Now, we can check whether 5 is a member of the A1 integer array, and this will return false. Similarly, we can check whether the hello string is a member of the A2 array, and this will return true. In both of these cases, the compiler is figuring out what the type t is. In the first case, it'll be integer. In the second case, it'll be the type string. And it makes sure that if type t is integer, then we're being passed in an integer for the first argument and an array event for the second argument. On the other hand, if we call isMember with 5 and A2, well, 5 is an int and A2 is a string, and those two don't match. So there's no way to pick a type t that will work for isMember, and so we'll get a type error here. Generics also supports polymorphic data structures. So here I've used an example from C++. C++ has a slightly different syntax for generic types. It uses a template syntax. Here we have a template for class Q, and the class Q is templated on an item class and a max items number. So we can actually be generic both in a number, which is the size of the queue in this case, or the maximum size of the queue, and the type of items that are in the queue. I've highlighted just the lines that are important in this example. Basically the lines that use the types, the type parameter item. So here, class Q declares an array of items, and those are of type item array, and it actually uses max items as well to size that array. Then we have two operations, NQ and DQ. NQ takes an item and puts it in the array, and DQ removes an array and assigns it to the item address passed in. We can later declare a queue of processes, or we can declare a queue of integers, and we can even override the default max items of 100 to store at most 50 items in our int queue. To understand what's going on with generic types, let's build a conceptual model. Here's the identity function in a little idealized language with generics. It's kind of like Java or maybe like a functional language, but we're going to be a little bit more explicit about generics than real languages are, just to show what's going on. And then we'll see how real languages simplify this a bit. So here we have identity, which is defined as a function that has a type parameter t, so it's generic in type t. It takes an x of type t and returns t. What does it return? Well, it returns x, right? An interesting fact is that absent unusual features like reflection, this is the only function we can use that takes a generic type t and returns an object of type t. We have no other object that we know is of type t, and so the only one we can return is the one we were passed in. Looking at this identity function, we say that it has the type for all t, t arrow t. So the for all t expresses that we can use any type. Pick any one you want. For all t's, this is a function from an argument of type t to a result of type t. Now, how do we use this again in our idealized language? Well, we can call identity, and we'll pass in the type parameter int, and then a value parameter 5, which is of type int. And of course, this will print 5. What I've done here is I've made the passing of the type parameter explicit. It's passed in these little angle brackets before the regular value parameters, but it operates in much the same way conceptually. If we want to describe this language formally, we can extend an expression language, like some of the ones we've been formalizing previously, in a way that defines and calls functions of generic type. So our expressions are all the ones we had before, addition and constants and things. But now we have a declaration of a function type with parameter type t, an argument x of type tau, and then a return type of type tau. And what does the function do? Well, it returns some expression e, which must be of type tau. Notice that type tau and the expression e can refer to this argument t inside them. We can also call functions like this with the syntax where we have an expression e to define the function, an argument tau for the type parameter, and another expression e for the argument. We will also extend the types in our theory to include a for all type. This for all type binds a generic parameter t that can be used in the argument and result types, which are just other taus from the language. That type t is also, of course, now a kind of type tau, because that's how we can embed it in these types tau. How do we actually do type checking of polymorphic methods? Well, here is a typing rule for polymorphic function definitions in exactly the same style that I showed. So here's the function we're type checking. Function, again, with type parameter t, a argument x1 of type tau1, a result type tau2, and a body of the function e2 that gets returned. So how do we type check this? Well, in the body of the function, we need to treat t like some unknown type. And so we add it to our context gamma. Our context gamma normally tells us what the types of all the variables are, but here it also tells us, okay, t is a type parameter. You don't know what it is, but assume that it's a type. So assuming that t is a type, and assuming that x1 has type tau1, we type e2, and we find out that the body of the expression has type tau2. That's got to be the same type as the result of the function, because after all, this expression is the body of the function. A small additional detail is that that type tau1 in the argument must be well formed, meaning that it only uses type variables that are in scope. We add these checks to various places in the type system to make sure that the types the programmer writes down are valid types. In this case, we need it for tau1 because that's one that the programmer wrote down. It turns out that tau2 will only be well formed if we can do the type checking rule, so we don't need to check that separately. Finally, the function's type expresses that for all type parameters t, all instantiations of that type parameter, the function takes an argument of type tau1 and returns type tau2. Let's look at a typing rule for calling that polymorphic function. So here, e2 is a function that we're calling with a type argument tau. Notice that most languages will actually infer this tau type argument automatically, so the programmer doesn't have to write it. But again, we show it explicitly here to simplify, to get a simplified view of how the type system works. How do we type check this? Well, first of all, we figure out the type of the function by type checking the expression for the function e2. If we find out that it has a for all type, for all t, dot tau1 arrow tau2, then we can apply this rule. We make sure that the argument type is well formed, and then we type check the argument type, the type of the expression of the argument, and we make sure that it matches the function parameters type tau1. A key issue, however, is that the generic type t is not in scope for e1. It's only in scope inside the definition of the function. So e1 won't have a type that includes t, even if the type tau1 used t. We can address this issue by substituting t with tau wherever it appears in the type of the function argument tau1, and then check that our argument expression matches the type after that substitution is done. Finally, the type of the function call is the return type of the function But once again, we must substitute the type argument tau for the type variable t wherever it appears in the function's return type, because again, when we call the function, the type t is not in scope. That's only used in the definition of the function. How do we implement generics? Well, there's a couple of different approaches. In C++ and Ada and some other languages, the entire generic function is copied every time that we instantiate the function with new type arguments. Basically what this does is it substitutes the type argument for the type variable, much as I showed you in that rule. This ends up duplicating code, and it has the disadvantage that it can create very large binaries. But on the other hand, it can be fast, as the code can be optimized with a particular type argument in mind. Another disadvantage of this approach is that type checking gets delayed until the copy of the code has been made. This adds some flexibility, because maybe a function doesn't type check for all possible arguments, but as long as you only call it with type arguments that type check, then it will work, you can use it, it will work for you. But what that means is that if there's an error in type checking your function, you'll only get that error when the function is actually instantiated with a concrete type in a call. Java takes a different approach. It reuses the same generic code for all calls to the generic function. The generic type data is handled indirectly through pointers. That's how we're able to use one piece of code for all possible uses, for all possible types. An advantage is, first of all, the code is smaller. We only have one copy of the code. And secondly, the function can be type checked separately from calls to it. But we lose some of the advantages of the flexibility and the optimization possibilities in C++ and Ada. Some compilers will make a hybrid where they'll do the Java-style checking early, but they might make copies of the generic function when it's useful to improve performance. C++ is an example of this strategy, although it generally shares code for reference types where you don't see a lot of those performance advantages, and makes copies for instantiation with primitive types where you typically do get larger advantages from making copies and optimizing those copies individually based on the type of the argument. Now, sometimes a function needs to make assumptions about the generic type. For example, what if we have to sort the elements of an array? Well, the elements of the array has to be a type that we know how to compare so that we can sort it. So in Java, we express this with a comparable type. Here we have a sort function declared in Java. It takes an array A of generic type t, but we constrain that type so it must extend the type comparable of t. Here, comparable is a class type that includes a compare_to method. What this means is that inside the sort, we can call compare_to, and we can see whether element I should come before or after element j of the array. Later on, when we use this, we can create an array of integers, here my array, and we can sort my array. And in Java, the type checker will figure out, first of all, that integer is the generic type that t should refer to, and it will verify that type integer actually implements the comparable type. In C++ and many other languages, we can declare local variables without actually defining exactly what their type is. So the auto keyword declares a variable, x in this case. We assign it to 3.5 plus 1, and x will have double because the right-hand expression, after some coercions, will have that type. We can also do global type inference, which allows us to not only emit types from local variables, but even from function declarations. In functional languages like ML or Haskell, the compiler can infer the types of functions. And that's very useful because these languages have lots of functions, and they have functions that are declared very locally, where it might be a pain to declare all their typing information. Let's explore just the intuition behind type inference using a simple example of a Fibonacci function, shown here in ML. Looking just at the intuition here, we have two functions, the Fibonacci function and also the internal helper function that is used recursively inside Fibonacci, as well as the arguments of both of these, the argument n to Fibonacci and the arguments n1, n2, and I for the helper function. Let's go step by step and see how these might be inferred. First of all, we observe that I has to be an int because it's added to 1 at line 5. ML doesn't have coercions between reals and integers, so real isn't a possibility. It really has to be an integer. Next, we can conclude that n has got to be an integer because we compare it to I. And in ML, we only compare things that have the same types. We can then observe that at line 6, all three arguments are integer constants. And so the things that we pass them to, n1, n2, and I, also have to be integers. Actually, we already knew what the type of I was. So this turns into a check that we're using I in the correct way. We knew it was integer, and indeed we pass in an integer, so everything's fine. Similarly, we'll check that the arguments to the recursive call at line 5, helper of n2, n1 plus n2, and I plus 1, each of those sub-expressions will form an integer, and that's consistent with the types we just inferred. Finally, since helper returns n2, which is known to be an int by the previous reasoning at line 4, then the return type of helper must be int. And so the result of the call to helper at line 6 will be int. And that means that since fib immediately returns the result of the call to helper, then the return type of fib must also be int. And so we're done. This is an intuitive view of global type inference. But if you look in the book, you can see a more detailed algorithm for how type inference is done. It's really interesting stuff. Go dive in. Let's check our understanding of generic type implementations. Summarizing our coverage of type systems, we've observed that types provide a number of benefits. Compiler-checked documentation about what we pass in as the type parameters to functions and what they might return. Types also aid compilation by telling us what operations to use based on the data types. And finally, they catch errors by checking whether we're applying operations to arguments of the right type. We found that subtyping determines how values can flow between types. We've looked at some of the trade-offs between nominal and structural type equivalence, where we have flexibility from the structural world on one hand, but then on the nominal side, we have a more clear reflection of the programmer's intent. We've looked at how coercions, which are inserted automatically in certain cases by compilers, and conversions, which are inserted by the programmer, move values between types. These operations check that the values match the requirements of the destination type, and they might transform the values to a new form as needed to make the conversion work. We also looked at how generic types can provide both flexibility to use a function with many different types, along with the safety that type checking provides. For more in-depth content on type checking and many other programming language topics, like and subscribe to this channel, and pick up a copy of our book.